Hello everyone, and welcome to 8th grade math module 7, Introduction to Irrational Numbers. In this video, we're looking at topic B, decimal expansions of numbers. Our learning goal is to make sure we can convert rational numbers between fraction and decimal forms. This will help us to master standard 8 NSA 1. Know that numbers that are not rational are called irrational. Understand informally that every number has a decimal expansion. For rational numbers, show that the decimal expansion repeats eventually and convert a decimal expansion, which repeats eventually, into a rational number. Now, for a lot of what we need to cover in the standard, we're actually just repeating skills from 7th grade. So in Module 2 of 7th grade, when we talked about division of integers, we explored the idea of terminating and repeating decimals. Terminating meaning decimals that stop, and repeating decimals being decimals that go on forever with one or more numbers repeating in the same pattern infinitely. So we will be seeing these again as we work in topic B. Another thing that we did is in Module 4, when we started working with percents, we did a lot of work with converting between fractions, decimals, and percents. So I have here a clip of the screen just going over how we convert fractions to decimals and decimals to fractions, which we will focus on doing in this topic. So remember, for fraction to decimal, you just do numerator divided by denominator, and that gets you your decimal expansion. If it stops, it's terminating. If you keep noticing the same pattern of numbers showing up in your decimal, then your number is going to be repeating with that pattern. And then to go from a decimal to a fraction, you would take all of the digits in your decimal number, write them, anything to the right of the decimal, in the numerator of your fraction, and the denominator of your fraction would be whatever the place value is of the digit the farthest to the right. And if you have a whole number in there, because it's a mixed number, the whole number can just sit to the side of your mixed number. And then everything to the right of the decimal point tells you how to make your fraction. And then I have here just the steps written out again, just a slightly different way. Numerator divided by denominator for fraction to decimal, and decimal to fraction. I mean, it's really just how you say the decimal if you use place value is how you write it as a fraction. So reviewing all that is important, but what's different at an 8th grade level? So let's focus again on those types of decimals. So those finite terminating decimals, they have a clear end, like 0.5, 5/10. But then there are infinite decimals that continue forever, and the ones that we are familiar with are repeating decimals. And I have 0.5 repeating here. That bar shows me that the 5 goes on forever. And then there's another type of infinite decimals that we don't talk about in 7th grade very much, called irrational numbers. You should be familiar with pi, which, like repeating decimals, goes on forever, but unlike repeating decimals, have no pattern. And the big thing with that is that it can't be written as a ratio or a fraction. So this lesson is just focusing on how we can write repeating decimals as fractions, and topic A goes more into those irrational numbers. So now that we know how to do all of our work with terminating decimals and fractions and converting those, what happens when we try to convert a repeating decimal? There are a series of steps that are sometimes intimidating, but still connected and straightforward if we take it slowly and think about it, that we can use to take repeating decimals and write them as fractions. And so here they are here, and then we'll try some together. So we're going to set our repeating decimal equal to x. We're going to move our decimal over until the first digit that repeats, or set of digits, are to the left of the decimal point. And then since we're doing that to keep our equation balanced, we'll have to multiply the x on the other side of the equation by whatever power of 10 represents how many place values we moved. So like if we move 2 decimal places, that would be 210 place values, so that's 100 times that we moved. So we would multiply by 100 to show that that's the same, because multiplying by 100 is the same as moving our digit 2 places to the right. And then in 3, what we would do is we would take those 2 equations and we'd actually kind of subtract them from each other by doing a repeating decimal being taken away from that value we get in step 2 after we moved our decimal point over. and then to keep it balanced, subtracting x from the x term. So just each side of those equations subtract away. And then after that, we have just an equation that's a one-step equation, and there are no repeating decimals left. So we use inverse operations to isolate our variable. And then that should end up just being dividing both sides by whatever coefficient was with x. Now, I don't know about you guys, but seeing these steps out of context doesn't really help me unless I know what it is this looks like and why I'm doing it. So I have two decimal expansions here that we're going to try these with. I encourage you to pause and look back at those steps from the previous problem and try this out. If not for this first example we're doing together, the second one after it, and then we'll revisit this. So my first step, if I'm trying to convert the 0.3 repeating decimal into a fraction, is I'm going to write that x equals 0.3 repeating. Now I'm going to write another equation, but instead of having my repeating decimal, I want to write a number where my repeating digits are to the left of my decimal, and only the one time. I don't want to move it much more than that. So what I'll do is I will move my decimal point one place to the right, because only one digit repeats, the 3. And moving it to the right is the same as multiplying this number by 10. And so on both sides of my equation, I'm really going to multiply my numbers by 10 so I get it to be the same. So since I did my 0.3 repeating times 10 is 3.3 repeating, then to keep it balanced, x times 10 is 10x. So this is fine here, and this is an equation, and I could try to solve this, but I want to get rid of my infinite decimal to try to write this as a fraction. So how could I get rid of my 0.3 repeating from 3.3? Well, I could subtract it. So that's what I'm going to do. But when I go to subtract from the right side of my equation, to keep it balanced, I have to subtract from the left. But 10x and 0.3 repeating aren't like terms, so it just make my equation more complicated. But as we already wrote, we set x equal to 0.3 repeating. So to take away 0.3 repeating, I could also write minus x instead, because x and 0.3 repeating are the same value. So now that I've done that, I can subtract those out, and I end up with an equation 9x equals 3. And this is easy, and I can work with this. I just need to use inverse operations to get my variable by itself. So since 9 is being multiplied with the x, I will divide both sides by the 9. And when I simplify that to a simplest form fraction, I get that x equals 1/3. So the beginning steps, a little bit different than what we'd be used to. Doing some substitution here of taking the x to replace with the 0.3 repeating that it's equal to, and then it gets me to this nice, easy to work with equation. So let's try that again, but this time with 0.5, and I encourage you, now that you've seen an example, to really pause and try it on your own. So just like before, first step, we're going to set our repeating decimal equal to x. Then I'm going to write an equation that's another equal balanced equation, but I want my repeating digit to be the left of my decimal point. So since I have to move my decimal point over one place, I'm going to multiply both sides of my equation by 10. So now that I'm here, what do I do to get rid of my infinite decimal? Well, I could just subtract away the 5 repeating, and then I don't have a repeating decimal anymore, I just have 5. But when I go to do that, I can't subtract away that 5 repeating from 10x because they're not like terms. But we said that 0.5 repeating is the same as x. So instead of writing it out as minus 0.5 repeating, I can write minus x, and it equals the same thing. I'm still doing the same thing to both sides, and I'm taking the same amount away. It just looks different. So once I've done that, and I subtract them away, I get 9x equals 5. And this is a one-step equation that you guys have been used to solving since 6th grade. So you do your inverse operation to get your variable by itself, and then you want to have that fraction in simplest form, which it actually already is, as 5/9. So again, a little complicated at first, but then it gets us to a very easy to work with equation. Now you may have noticed something similar about those two examples that we did, and here are a set of other repeating decimals and their fraction forms, and you might notice that just about all of them are written with 9s in their denominators and nothing else, either 9 or 99 or 999, a whole bunch of 9s. And so that brings us to a shortcut that we can use when we are converting repeating decimals instead of doing the full equation. So what we can do is we gotta first keep track of the number of digits that repeat. If one digit repeats, then you're gonna put that number in your numerator and your denominator is just gonna be 19. If two digits repeat, put those two digits in your numerator and your denominator will be 2 9s, 99. Same thing with 3 digits, 4 digits, and so on. So the number of digits that repeat, they all go in your numerator, and then that many 9s go in your denominator. So let's try one last example with a more complicated fraction. So we have a digit other than 0 to the left of our decimal point. We have more than one digit repeating. And if we use our shortcut, we can just pull our whole number to the side because it won't be part of the fraction anyway. And then for the 25 repeating, we would just take the digits that repeat, 25, put them in the numerator, and then in the denominator we would put as many 9s as there were digits that repeated. So since 2 digits repeated, it would be 99. So let's see if that works with what we get when we use our equation method. So just like I said above, for using the shortcut, since this is going to end up being a mixed number, I can pull my whole number to the side because 2 is just going to be 2 in my mixed number. And then I can see what 25 repeating would be as our fraction. So I'm going to set x equal to that 25 repeating. And then I'm going to move my decimal over so that my first set of repeating digits is to the left of the decimal point. Since that is 2 spaces, I'm really just multiplying by 100, and I have to do it to both sides of my equation to keep it balanced. But now, how can I remove my infinite decimal? I mean, I just need to subtract it away. But to keep my equation balanced, I have to do it on both sides. And since I can't take 25 repeating away from a term with x in it, instead, I'm just going to put minus x because x is equal to 0.25 repeating. So when I subtract that away, I'm just left with 99x equals 25. And when I solve that using inverse operations, I get that x equals 25 over 99. So that's the decimal part of my repeating decimal turned into a fraction. And then I join it back with its whole number of 2, and I get the mixed number of 2 and 25 over 99 as my ratio version of 2 and 25 repeating. What does this make you wonder about trying to convert repeating decimals into fractions? Write your questions down so you don't forget them. Then you can try to find answers online or ask a classmate or teacher. Thanks for watching, and when you're trying this on your own, remember, if you learned from your failures, then you succeeded.